right, welcome everybody. It's great to be back here. Fifth conference. Hopefully the first one was going the last mile and for energy calculations and drug discovery. Hopefully we have a shorter than a mile to go at this point. But just introductions. First is my group climbing some of the mountains around Boulder. Particularly, Eric Diebeck did a lot of the work doing direct MD free energy calculations that I'll show. Naden on quasi-harmonic approximations, and Natalie on some of the incorporating quantum mechanics into this. So, and funding and a lot of collaborators who do some more sophisticated, well, some alternative ways of approaching this that are very valuable to have those insights. So. Stability prediction in crystalline materials is critical to evaluate commercial stability. Beyond drug design, so many materials have multiple metastable crystalline forms or polymorphs. Small organic molecules tend to have a lot because there's a lot of ways to pack them in. Polymorphic phase accept properties such as optical properties of dyes, strength of properties of cement, charge transport in semiconductors, detonation properties in energetic materials, as the DoD likes to call them. So this is really a larger problem, not just drug design. But of course, we're interested in drug design here. And so predicting crystal polymer stability is important in drug formulation. Rotigotine, which is a Parkinson's drug, was administered a transdermal patch. But it turns out that the formulation, form 1, over time it rearranged into you get crystals forming of form 2, which they did not know about beforehand, which is insoluble, had to be taken off the market for 4 years until they could reformulate it in a way that it could be delivered, that it could still be delivered. So, different polymorphs can have different bioavailability, but also in processing, particle size, the amount of water it takes up, dissolution rate. All of these things are affected by the polymorph. And some characterization of the polymorphs is really necessary for for FDA approval. So how do you predict this experimentally? It's kind of hard to do. You've got a lot of different ways you can vary the conditions to try to induce different polymorphs. Cooling a solution, evaporating solvent, but then you have choices of evaporating solvent, thermal annealing, slurring experiments. There's mixing with various things. There's a lot of things you could do, but my graduate student was a secret shopper, went around trying to get some quotes, pretending he was from a company. And so usually it costs $40,000 to $50,000, whatever, but 6 to 7 weeks and 4 to 6 grams of material. So this is something that we'd love to have some sort of screen beforehand in order to understand before we make the molecule, especially before we make it in large batches, what the behavior will be. So this is a fairly common field now, it's computational crystal structure prediction. Cambridge Crystallographic Structural Database has competitions every now and then to try to do blind predictions of these. But virtually all of the methods use essentially lattice energies. They're brute force searches of all the different ways you can pack these molecules into their and just determining what the lattice energy of that is. And so there's been a lot of work at doing force fields specifically for that molecule, doing what level of quantum mechanics do you need, and so forth. And they often produce far too many candidate structures. If you're lucky, you'll get a prediction down here, and the other predictions will be the experimental structure is the yellow square. If you're lucky, it'll look like this. Your predicted one with the lattice energy will be well below. This is far more common, where you have a number of candidate structures, possible packings, and the experimental structure, most stable structure, is somewhere there. But sometimes you get things like this, when your experimental structure has really no relationship to your predictions at all. And like I said, they're currently based on lattice energies, but really, how much does entropy matter? So that was our main research question here. Is the entropic contribution to the free energy nearly negligible? And are some more approximate methods good enough to calculate the entropies there? So we specifically started looking at systems where we know that the standard approach fails. These are all systems that have one stable polymorph at low temperatures and another stable polymorph at high temperatures. Lattice energies are therefore insufficient to capture which one is more stable over the entire temperature range. So hopefully we could at least say, yes, all of these become destabilized at higher temperatures. And so what we did is we ran simulations at a series of temperatures. Just looking at 300K, do you think entropy is important for the stability of this crystal at 300K? This is when the visual test is like, yeah, that's wiggling around. So, and then we carry out simulations at a range of temperatures and use multi-state reweighting to produce a smooth curve of the free energy as a function of temperature. Now the problem is that you get a very good prediction for the model of the free energy as a function of temperature along that line, but you don't have any way to connect the surfaces of the two different polymorphs together. That's what we need. So what we do is we use thermodynamic cycles where we restrain the polymorph, turn off the interactions, and then we can make a correction in the ideal gas form between the two polymorphs and take it back out. So this is a fairly, and this is very similar to what you might see in ligand binding. It's the same idea. Takes a fair amount of work, but that gives us a very accurate measure of the difference in the free energy between the crystal polymorphs at one temperature. So if we have the full temperature for each of the polymorphs, we have one place to connect the two surfaces, then we can calculate the free energy difference between the two polymorphs at any temperature. And so what do the results look like? We get nice smooth curves of free energy as a function of temperature, and we do see, and this is typical for all the molecules, we were able to, even at point charge potentials. And this is one, you don't get one thing that's pretty well known now is that you can't really get away with fixed charge potentials to make good predictions in solid materials because you lose all this conformational averaging. Things are sort of locked into position. They do polarize, and you don't lose the polarization as it reorients. But even with just OPLSAA, we were able to get that all of them did indeed melt and switch from the one form to the other. That's sort of what the result coming out would look like. And we find that the entropic term can be significant at room temperature. So right here I've got sort of what sort of a criteria for what is a big enough free energy difference to matter, about 0.1 kcal per mole. One important thing is that small free energy differences make a big difference because the kinetics of the solid form are so slow. If you just have a block of a crystal here, it will never go, that is kinetically trapped, it will never go to the more stable polymorph. Usually the way this happens is it dissolves and then recrystallizes in a different form. And so you do have to worry, if you find any polymorph that is measurably more stable, that is a polymorph, or even one that's less stable. Just because you crystallize something doesn't mean it's the most stable. It could be relatively high, half a kcal mole or more in free energy, but will be very kinetically stable. So you have to worry about all of these small differences and the existence of polymorphs with these small differences. So generally, using some criteria that other people have used, at least 2/3 of these have entropic differences that need to be taken into account, that a pure lattice prediction would not get these right. And it's particularly interesting, a couple molecules, and these are small enough that they're a little less applicable, is that these actually have one phase that's disordered, where they have some sort of orientation, even though they're locked in position, so it's still a crystal, they have orientational freedom. And there, obviously, entropy matters quite a big deal. But if you look at some of these, the ones that have significant entropic differences tend to be the ones that start looking more drug-like, though even the drug-like ones are on the small side here. A lot of the crystal structure prediction methods are limited to 2 or 3 rotatable bonds at max, which is obviously a big a big limitation. So another interesting thing is that the temperature-dependent changes in enthalpy are not negligible. Because there's a decent amount of conformational motion, you get that the enthalpy at 300K minus the enthalpy at 0K, the lattice energy, is pretty significant. In some cases, as comparable to entropy. For example, in this case, why does that molecule have an entropy difference that's so large at one temperature? No, that's something we've not quite figured out yet, but that's pretty clear. So how do computational estimates of the energy and the entropy compare to experiment? So this would be the predicted delta H using OPLSAA. The error bars are quite small there. They're not shown because they're small in simulation, and they're not shown experimentally because nobody bothers to calculate these give good estimates of these uncertainties experimentally. So probably at least on the range of, for enthalpies, a third, half of a kcal. So what you see is that OPLSA is not very, and any fixed charge potential, it's not just OPLS, is pretty bad at predicting enthalpy of crystals. This is why a lot of people doing crystal structure prediction have really driven towards using quantum mechanics in order to get these right. But if you look at the entropies are all much closer. They're all in the same quadrant. Correlations are not perfect, but they're much better than the enthalpies, which is quite interesting. So this takes a decent amount of work, a few hundreds of CPU hours. So is there an easier way to calculate the free energy as a function of temperature? So one method that is commonly used in solid state and is starting to be used more in sort of metallic, material science solid state, it's starting to be used more in crystals, is a harmonic approximation. If you look at this, you say, do a first approximation, and just sort of jiggling around there, around the same central point, so maybe we can treat this harmonically. And so in this case, you can approximate the Helmholtz free energy as the lattice energy plus a harmonic contribution, where you can calculate the Hessian, get the vibrational modes out, and just do simple analytical statistical mechanics from that. Sort of expensive, but calculate a Hessian, although you have to get that out of your code. But that's relatively cheap for a single conformation. And then you approximate the free energy as, I should have added a PV there, but that's trivial to add, the lattice energy plus this vibrational energy. So one step further that you can take is what's called a quasi-harmonic approximation. Lots of ways to be quasi-harmonic. Biophysics also has a quasi-harmonic approximation that's fairly different. But in this case, what we're doing is, the short version is you expand the unit cell and find which volume gives the lowest free energy at each t. As you expand the cell, your lattice energy becomes less favorable, so things are spaced a little more apart, but your entropic term becomes more favorable. So at each temperature, the cell will expand. So you have this minimization problem, and basically you have to expand the cell stepwise and energy minimize the coordinates at each volume, and then calculate the Hessian at each volume. Technically, you're required to calculate the Hessian each volume, but it turns out that there's some fairly accurate relationships that relate the vibrational frequencies at one volume with the vibrational frequencies at another volume. So usually people just do calculate a couple Hessians to calculate the linear parameter for each wavelength, and that's a lot of people that say that works. It's a common assumption to make, and it works relatively well. So this takes an order of a few CPU hours instead of dozens of CPU days. So how much does this help? Well, it turns out that for small rigid systems, it actually works pretty well. Most of these differences, except for this, are all less than that 0.1 kcal per mole. So for small molecules that are not quite yet drug-like, then a quasi-harmonic approximation appears to be all that you need. Once you start getting to larger, more complicated molecules, then you start seeing deviations that are not that are large, that start being significant. Of interest are actually some of the biggest deviations are cyclopentane and succinylnitrile, which do have disordered forms. So the more opportunity there is for disorder, in this case, looking at the structures, it's fairly clear that some polymorphs have space where the alkane can move around, and some polymorphs don't. That's an example of a difference where a harmonic approximation does not work. And we understand the same thing for tolbutamide. This alkane chain has some polymorphs so it can wiggle and some where it can't. So the quasi-harmonic, this is just showing that the final results, that they're reasonable for rigid molecules, less so for flexible and disordered molecules. Is one problem that we aren't including anisotropic expansion. The usual way to do quasi-harmonic analysis is to isotropically expand the crystal, but which works as a decent approximation for a lot of metals, metal oxides, etc. But for organic molecules, they have anisotropic shapes. They tend to expand. You could have, rather than like all the box vectors going up by 3% when you raise the temperature by 100 degrees, you could have one that increases by 6% and another that shrinks by 2%. And so this is something that it's fairly hard to do because you can't expand, you can't do a grid search in 6 dimensions to to see which of those box shapes will give a good, will give the lowest free energy. So we took a look at this as essentially, this is a minimization problem. We're trying to minimize some function over, could be the box volume, it could be your set of box vectors, or maybe you can parameterize things in a single parameter. And so you can look at this minimization problem, and what you can show is that the change in volume with respect to temperature can be written in terms of a change in entropy with respect to volume and a second derivative of the free energy. But then this generalizes to multiple dimensions as well. So essentially, in this case, this would be, instead of expanding isotropically, you expand linearly in each dimension. You say, I'll assume that they all just scale. Once I determine how it's changing at 0 Kelvin, I just assume it goes linearly up that way. So that's one way you can do an anisotropic expansion that way. So these are ODEs, so we can use standard numerical techniques to start at 0 Kelvin, calculate these derivatives, and just integrate up what that volume would be. So instead of doing, for anisotropic expansion, a 6-dimensional search, we can, if you're writing down the equations, don't worry, it's posted on archives. You can just copy everything there. So I'm not explaining all the details here, but we'd use some tricks for applied math in order to be able to solve, give the information at given point, solve the direction that we have to expand in. So, so this linearized, so I mentioned, just assuming that it's linear and integrating up that way. That works pretty well. So here's some of the what we've done. So what you see is, first of all, we can find that in many cases, so here the gamma here is using the Gruneisen parameter approach. That has some differences. For Source, all the difference between QHA and HA is pretty small. We're still generating the data for the others. Doing a full 6-parameter search and doing just a linearized 1D version works pretty well. You can see these lines are essentially on top of each other. So I might only present some data for the 1D anisotropic expansion. Okay, but what we see is that even anisotropic expansion may not explain much of the gap between the molecular dynamics and the quasi-harmonic approximation. So what I have here, I have a radar plot where I have the A, B, and C box vectors and the 3 angles as well. And so isotropic expansion is the green shape, and blue is the MD. So our anisotropic approach allows us to expand in essentially the same way MD expands. That's a full MPTA simulation. But if you look at the free energy as a function of temperature, here I've got MD in blue, 1D anisotropic. In this case, it gets about half of the distance between them, though they're not that big differences. But if we look at some other molecules, here we still get very good matching of the anisotropic expansion. But in this case, the isotropic expansion approximation was actually right on what molecular dynamics was, but the 1D anisotropic expansion gets worse, even though the box vectors are correct. So there you had essentially a cancellation of error. Another example where MD had some interesting results because you started to have some entropic freedom in this more complicated molecule. The box vector expansion is predicted exactly right, but really it doesn't make much difference in the free energy at all. So that's not really where it's coming from. As I said, I think that most of the anisotropy comes from non-harmonic motions of the small molecules. Here's one of the extreme examples. I've got one polymorph of cyclohexane here. You can see it's pretty crystalline. But then when we go to higher temperatures, then a different phase of cyclohexane becomes more stable. And you can see the molecules are moving around. They're staying in their locations, but they're much more free to move. And so at higher temperatures, this is the more stable structure, more stable crystal. Some interesting effects of these lattice minima can essentially interconvert at higher temperatures. There's a lot to unpack here that I only have a couple slides that we'll go through this, but it is interesting. We can start seeing what some of the conformational heterogeneities are and start understanding the source of some of those entropies by looking at these restructurings. So how does this entropic story change when we increase the detail of the energy function? We know that to get the lattice energies right, we need more accurate Hamiltonians. So you could go to multiples, polarizability, which people are certain that you need at least that level to get good predictions, or all the way to quantum mechanics, which some people are doing too. They're doing DFT on many of the structures they generate. So this is what I've talked about. We have a good sense of how to do this. People have been studying this direction for a while, just for lattice energies increasing. What about this? What about entropy with higher levels of theory? So we're using some alternate pathways to do that. If you were just to calculate the free energy purely polarizable, it's pretty expensive. But what we can do is calculate this full curve with a cheaper point charge model and then correcting at the endpoints. So there, maybe it's 10 times more expensive polarizable, but the corrections for this particular case I'm showing end up being pretty cheap. And so this is the way that we approach this. For this, we've only done benzene. We're working with Mike Schneiders to generate more data for the rest of the data set using some other techniques. But what we see that, for example, for benzene has 3 polymorphs, for benzene 1 and benzene 2, interestingly enough, there's a enthalpy difference between them, but the entropies are almost exactly the same, whether you're looking at OPLS or amoeba, which is quite interesting. If you look at now, if we look at the free energy difference between benzene 2 and benzene 1, in this case, there's actually a significant entropy difference between the 2 levels of theory. But interestingly enough, if you look here, the benzene 1 minimum energy structure, the box vectors change, the crystal packing changes significantly. Even though they're still roughly in the same place, the lattice structure has changed. And so one thing we're seeing right now, though we don't have enough data to show it, is that if the structures are essentially the same, the entropies are relatively independent of the force field. However, if the minimum energy structures change, obviously you're going to have different entropies. So the source of entropy doesn't occur for the vibrations are similar, but the different structures will lead to different vibrational minima. We started looking at this with quantum mechanical approaches. In just the harmonic approximation so far, this data is still being the project is still underway, so I only have, again, benzene, but we're looking at QHA and more molecules. And we see the exact same pattern. There's a quite large of a difference, and this is DFT D3 PBE pseudopotential. What we see is that for the free energy difference at the quantum mechanical level between polymorphs 2 and 3, which also, it's the exact same pattern, that the polymorph 2 and polymorph 3 are relatively similar between, the box vectors are the same, the arrangement of the molecules is relatively similar with all 3 levels of theory, but polymorph 1 has quite different box vectors with all 3 levels of theory, and here, the entropy, so a lot of the differences, the data is still being processed, but the pattern appears to hold going up one more level of theory with the same molecule. Benzene's pretty small and symmetric. There could be differences there that we're still tracking down. So the conclusions here, point charge potentials are significantly better at predicting entropy than entropy. Better enough. We have a lot of anecdotes now, but we need to keep generalizing it, see if we can generalize that to see if it holds for more systems. Perhaps. I'm not claiming, nowhere in here I'm saying we're doing crystal structure prediction. We're doing some fundamental thermodynamics that hopefully can help crystal structure prediction in the next step. So this is the hypothesis that this initial data is suggesting might be the case, needs to be tested, that the entropy is far less important. And anharmonic contributions are significant for flexible and disordered molecules. Just treating the anharmonic expansion is not sufficient to get that. Some reweighting enables fast estimates of delta S and delta G and more expensive potentials. We're looking at some other approaches as well. The change in entropy is relatively insensitive to functional form unless the minima are structures. Is the story general is what we really want to address. So I do want to put a couple advertisements in. One is recruiting for 2 postdocs. One is for this open force field initiative. And this is actually it's a joint position starting with the open force field initiative and eventually moving to Crystal Pi. Job's been posted, it's out there. Come talk to us at lunch about this. This is actually with any, even though we're the ones in open force field doing crystal structure prediction, this particular postdoc is decoupled from that, so you can work with any of the PIs in this. So if you're interested in that, please come to lunch. Also, myself, I'm recruiting a postdoc for developing new theories for designing non-biological heteropolymers with secondary structures. Things that fold up like proteins but aren't proteins. What I think is particularly interesting, right now this is looking at the sort of the underlying theory, but I think the applications for drug design are pretty interesting. Potentially new scaffolds for peptidomimetics. Contact me directly if you're interested. If for open force field, come to lunch with us after this, and contact me directly for the second postdoc. I'd love to talk to you if this sounds interesting, making things that look like proteins but are not, that have extra things stuck in there. And one other ad I want you're gonna give me time to do this one. So in a talk yesterday, there was a comment. I'm confused about how difficult postdocs and graduate students find it to calculate a binding for energy. I am not surprised. It took me a long time to figure out how to do it right. And so one effort that David Mobley and Dan Zuckerman, who are both here in the back, are helping get involved with, and a lot of you are already involved with, is this idea of the Living Journal of Computational Molecular Science. And it is a peer-reviewed journal for papers that can and should be updated, such as reviews, descriptions of best practices, comprehensive tutorials about how to do things. I think this has a potential to really, we're still getting, the first issue is planned for fourth quarter this year. So we're in the process of dealing with the first submissions. And I think this has a potential to be a really cool thing that can help solve these sorts of problems. You have a complex problem. You really need the efforts of the entire field to come up with good ways to iteratively improve the right way to calculate these things. So happy to talk about that as well. Send me email or inquiries about that. So thanks very much.
Those of you interested in live comms should find Michael or David or Dan during the break before they find you. Questions? Quick questions.
Yeah, so on the benzene one, I don't think it's benzene one, so the structure is known. So
Yes.
Of those three methods, they all seem to change the structure.
Yes.
Which one?
Somewhat.
You didn't mention what, does the ab initio do the
I'd have to, usually ab initio does the best. I have to go back and check what the RMSDs are. And this is data that just hot off the press, and I didn't tell them to check that. But yeah, usually ab initio MD does decently well at finding the experimental structure. Because the experimental structure is not always at 100 Kelvin. So, but usually what you can show that with a sufficiently high level of theory, you can get the lattice energies pretty close. So that's generally the better.
If the structure's wrong, then that all goes out.
Yeah. So that's the interesting thing. It's like, is the right thing to do to use quantum mechanics to get the right structure, and then tack on a lower level of theory to calculate other things, which very well could be the case.
Michael, that was very interesting. I didn't really get a sense of how big were your simulation systems relative to the unit cell.
Great, an excellent question. So we generally were simulating maybe 8 to 12 unit cells. Yeah. 8 to 12. There's some 1/n limits here, but those are pretty well understood. So.
One quick question from Darren, and we have to move on.
Okay, just real quick for thermodynamics in the solid state. Could you make a comment of the importance of zero-point energies according to nuclear degrees of freedom, and also the importance of kinetic versus thermodynamic solubility?
Excellent question. So in terms of zero-point energies, our comparisons between methods were done purely classically. The zero-point energy can contribute to expansion at low temperatures, but what we've generally found is that once you get above 50 Kelvin, it's irrelevant. In terms of kinetic stabilities, that's kinetics of solids and thermodynamic solids are both extremely important and cause really completely separate formulation issues. So understanding both of those things is very hard. Thermo was far easier because the problem with kinetics is that the kinetics are different depending on what you're doing, what the solute is, what the solvent is, what the conditions are, whether you're grinding it. And thermodynamics is the same regardless. The kinetics is different in every single situation. So that's something that is much harder to model, and other people are banging their heads against it and making
decent progress, but this is not that.
All right, let's thank Michael again.